Okay, so good day everyone. I will be discussing the exercise 10 of Chem 32.1 entitled UV-Vis Spectrophotometry. So before we proceed, let's have the learning objectives of this exercise. First, you have to study the internal mechanics and light path of a single beam spectrophotometer. Determine the wavelength of maximum absorption by plotting absorption curves by some substances. Okay. Next, prepare a Beer's law plot for a given analyte. Next, illustrate deviations from the Beer's law plot and determine the amount of analytes in a given sample by spectrophotometry. Okay, so before we proceed, let's define what spectrophotometry is. All right, so it is a method of analysis based on the interaction, absorption, or production of light by matter. Okay, so suppose we have matter here and it has an interaction with light. So that interaction produces a certain response. At yung response na yun yung kinukuha natin sa spectrophotometry. It may also include the interaction of electrons, ions, or acoustics with matter. Okay, so for Exercise 10, will we be focusing on UV-Vis spectrophotometer. So this is an instrument that measures the concentration of a given analyte on a sample based on its characteristic absorbance. So this UV-Vis spectrophotometer, so kapag tinawag natin UV-Vis, usually yun na yung UV-Vis spectrophotometer. So we have two types of UV-Vis. So we have the single beam spectrophotometer and the double beam spectrophotometer. So later on, we will discuss more on the difference between these two. Okay? So before we proceed, let's have the major components of the spectrophotometer. So we have here the light source, the monochromator, the wavelength selector, sample holder, detector, and readout system. So itong 6 major parts na to, ito yung 6 na pagkakasunod-sunod nila on a block diagram. For example, these 6 components are designed on a linear manner. Okay? Sabihin, laging nandito yung light source natin, and ang kasunod ng light source always is the monochromator, followed by the wavelength selector, followed by the sample holder, followed by the detector, and followed by the readout system. Okay? So, iisa-isahin natin kung ano ba yung ina-encompass ng bawat major components ng spectrophotometer. So first, let's discuss more about the light source. Okay? So light source, it can either be continuous or discontinuous. Okay? Yung continuous natin, it produces a spectra over a broad range of wavelength. Examples of continuous light source are tungsten lamp, deuterium lamp, and xenon arc lamp. Okay? So itong mga continuous light source natin, these are usually the ones that are present in our UV-Vis. Okay? Next, we also have a discontinuous light source. Ang discontinuous naman, it produces a specific wavelength. So in contrary with the continuous, suppose we have here a spectra of light. Kunwari from 700 to 350 nanometers ang wavelength. Yeah. So meaning to say, on this wavelength, ito yung pinoproduce ng light source natin from 700 to 350 nanometer. Whereas kapag naman discontinuous, for example, ang pinoproduce lang niya ay 465.9 nanometer. So, specific yung wavelength na pinoproduce ni discontinuous. Okay? An example of discontinuous light source are the following. So we have the hollow cathode lamps or the HCl, electrodeless discharge lamps or EDL, and the lasers. Okay? So the mga discontinuous na to, these are used in other types of spectrophotometers. So dito sa atin, sa UV-Vis, hindi natin ginagamit yung HCl. Sa UV-Vis kasi ang ginagamit natin ay tungsten lamp or yung W lamp. W kasi yung tungsten. Then we have the deuterium lamp or the D2 lamp. So sa exercise natin, makikita natin yung tungsten at deuterium lamp when we do our experiment. Okay? So what are the differences of tungsten and deuterium lamp? So yung deuterium lamp natin, it provides light in the UV region. Okay? So UV region natin ay from 190 to 400 nanometers. So take note kapag dito, siya ay for UV region. So yung tungsten filament lamp naman natin, or yung W lamp natin, yun naman ay for the visible region. Ang visible region natin ay from 350 to 2,500 nanometer. Yung 2,500 nanometer, yun yung near IR region na. Okay? So this is the visual example of the tungsten filament lamp. Okay? So we also have another type of continuous light source, which is the xenon arc lamp. Yung xenon arc lamp naman, it can provide light in the UV and the visible region. Yan. So ulit, ang ating D2 ay for UV. Ang ating W ay for visible. Ang xenon arc lamp ay for UV and visible region. Pero mas expensive kasi ang ating xenon arc lamp. That's why usually yung mga instrument natin, they have two lamps, which is the D2 lamp and the tungsten lamp. Okay? So this is the visual example of our xenon arc lamps. Next, we have the example of discontinuous light source. So ito yung example natin. Na yung discontinuous, it only provides a certain wavelength of light. For example, if we want to analyze zinc, it is only available for 213.9 nanometer. So if you're going to use zinc, or if you're going to use or analyze zinc, you have to make use of these hollow cathode lamp specific for 213.9 nanometer. Okay? So next naman natin ay after the light source, your light will pass through a monochromator. Okay? Kasi yung light natin ay polychrome light na yan. Polychromated light. Okay? So gusto natin, certain wavelength of light only passes through our sample. So your polychromated light will have to pass through a monochromator para ma-disperse yung ating light into its separate wavelengths. Okay? So we have several types of monochromator. First, we have the prism. Ayan. So the prism monochromator, so yung ating polydispersed light na white light, kapag pumasok yan sa prism natin, so nagkakaroon tayo ng refraction of light. Okay? So the specific wavelength of light is based on refraction phenomena. So nagre-refract yung light, so nagkakaroon ng dispersion of wavelengths. Okay? So for example, gusto lang natin ay yung wavelength for red color. So possible na natin siyang makuha kasi na-disperse natin yung light from the white light by means of using prism monochromator. We also have another type of monochromator. So take note ang keyword natin dito ay prism is based on refraction phenomena. Because yung next nating monochromator is grating monochromator, which is based on diffraction phenomena. So yung light source natin, papasok yan sa entrance slit, and the light will be passed through to our collimating mirror. Tapos, meron tayong diffraction grating dito. Yung diffraction grating natin, pag zinong in natin yan, meron yung mga grooves. Okay? And these grooves, or yung mga gratings natin, will allow the diffraction of light into its separate specific wavelengths. Then by then, we can choose kung anong wavelength ba yung gusto natin. Yung wavelength 1 ba, wavelength 2, or wavelength 3. Itong wavelength na to ay, when we read it, it's just lambda. Okay? Lambda. Alright? So, from our major components, so we have the light source, followed by we have the light source, followed by the monochromator. Then, yung monochromator natin, kapag polydisperse na yung light natin, meaning to say, from light source na white light, magkakaroon tayo ng different wavelengths of light. Tapos, pag nag-separate na yan, followed by the wavelength selector. Wavelength selector. Usually, yung ating monochromator at wavelength selector, sometimes they are just one component. Pero to make things more easier to understand, so once magkaroon ng polydispersed light, papasok na yun sa wavelength selector. Tapos, once you have selected your preferred wavelength, ang next nating step ay yung sample holder. Okay? Ayan. So, ito yung example natin ng sample holder. So, ang sample holder natin ay tinatawag nating cuvette. Okay? So, we have 3 types of sample holders. So, we have the glass or plastic cuvette, we have the quartz cuvette, and we have the sodium chloride or potassium bromide cuvette. So, ang differences lang nito is kung kailan sila dapat gamitin based on the wavelength or working wavelength na gagamitin natin. So, for example, if we're going to use visible region na wavelength, so, sa pag-visible, ginagamit natin ay glass or plastic cuvette. Okay? Pero kapag gagamit tayo ng UV, tsaka visible, so pwede natin gamitin yung quartz. Okay? So again, kapag yung ating wavelength of interest is on the UV region, gumagamit na tayo ng quartz. Pero kapag visible region, pwede gumamit ng quartz or pwede gumamit ng glass or plastic cuvette. Pero kapag UV lang, hindi mo pwedeng gamitin yung glass cuvette. Okay? So if you're going to use a wavelength higher than the visible region or around IR region na yan, gumagamit na tayo ng KBR tsaka NaCl cuvette. Okay? So first, we have the light source, monochromator, wavelength selector, sample holder. Next naman natin dito is yung detector. So once the response is detected by the detector, babasa na natin yung response via the readout system. Readout system. Okay? So these are the 6 major components of your UV-Vis spectrophotometer. Next naman, as mentioned kanina, we have 2 types of UV-Vis. We have the single beam and we have the double beam. So ito example ng ating double beam. Okay? So we have the light source. Yan. Light source natin ay yung deuterium lamp or the tungsten lamp. Then papasok yan sa monochromator. Okay? Tapos, dito sa axis slit natin, andito na yung ating wavelength selector. Then once makapasok na yung wavelength of interest natin, so we have beam splitter here, wherein yung sample natin ay matatamaan ng light na galing sa monochromator, and yung reference sample cell natin ay, or reference cell natin, ay matatamaan din via the light splitted from the beam splitter. Okay? Itong photodiode natin ay the detector. Okay? Then, once ma-detect ng detector yung light, papasok ko siya sa ating readout system. So dito kasi, if you want to make use of, if you want to correct your okay, so if you want to remove the effect of the matrix or the diluent of your sample, kasi ang gusto lang kasi natin ay makuha yung absorbance from our analyte. Ito yung goal natin. Makuha natin yung absorbance from our analyte. And take note, yung ating analyte ay, for example, gusto natin ay copper 2+. Copper 2+. Ayan, kunwari copper 2+. Pero yung copper 2+ na yan ay naka-dissolve yan to a certain solvent or diluent. Di ba? So, meron kayong use of diluent. Or yung solvent, kung saan siya naka-dissolve. So to make sure that yung absorbance na makukuha natin ay dun lang sa copper 2+, sine-check din natin yung absorbance ng diluent natin. Yun yung reference natin. Absorbance due to solvent. Okay? So kasi ang makukuha kasi natin dito as yung sa sample natin ay absorbance ng analyte plus absorbance ng solvent. So this is the total absorbance. Then ang makukuha natin sa absorbance to solvent ay absorbance ng solvent lang. So to get the absorbance of the analyte, so we get the total solvent, total absorbance, i-minus natin yung absorbance from the solvent to get the absorbance of the analyte. So ito yung concept ng double beam spectrophotometer. So kailangan may dalawang cell tayo, ilalagay na natin sa cell natin yung solvent natin, kung ilalagay natin sa cell yung sample natin, then yung makukuha nating absorbance dito is the corrected absorbance already. Meaning to say, yung analyte na lang yung nakukuha natin. Okay? So next naman natin is the single beam. Sa single beam naman, ganun lang din yung mechanism niya, except walang reference cell. Ibig sabihin, you can imagine na wala itong part na to. So itong part na to, ito na yung single beam. Okay? Tinanggal lang natin yung reference. So how do we check or how do we correct yung reference natin? I mean yung blank natin when we make use of single beam. So ginagawa natin dito is we correct the absorbance. What we usually do is first i-read natin yung blank natin. Yung blank natin yan yung usually solvent natin. Okay? So pag na-read na yan, next natin i-read is yung sample. So pag na-read na si sample, kung ano yung absorbance dito, absorbance 2, ito ay absorbance 1. So to get the absorbance or the corrected absorbance for the analyte is just abs 2 minus abs 1. Ima-minus lang natin siya manually. Whereas dito sa ating double beam, na-minus na siya automatically. Okay? For the double beam or for the single beam, it is just you have to get the difference manually. Okay? Next is the governing principle of spectrophotometry is the Beer-Lambert's law. It states that the measured absorbance is directly proportional to the concentration of the absorbing species. Okay? So yung I natin is yung light. Yung light ha. Yung initial or incident light. Then ito yung nag-pass through na light. Okay? So it just states mathematically that A is equal to ABC. So basically madali lang, no? And very madaling tandaan. Yung capital A natin is the absorbance. Yung small letter A natin is the absorptivity. The small letter B is the path length. And the small letter C is the concentration. So doon sa ating Beer-Lambert's law, it states that the absorbance, which is the capital A, is directly proportional to the concentration, which is the small letter C. But there are certain factors that may affect this relationship. So ito yung ating absorptivity, which is unique to the absorbing species, and the path length, which is dependent on the dimension of your sample holders. Okay? So itong ating Beer-Lambert's law, it also has its limitations. So we have the real deviation, the chemical deviation, and the instrumental limitations. So first, let's deal with real deviation. Real deviation is due to the assumption of the law itself. Okay? So in law itself, di ba, we mentioned that the absorbance is directly proportional to its concentration. But this only works to dilute solutions. Okay? So if you're going to plot a certain concentration, absorbance versus concentration. Yeah. So there is a working range that the absorbance and the concentration is linearly correlated, but there will come a time na magpa-plateau yung ating plot. Meaning to say, hindi na linear yung relationship ng concentration with the absorbance. So yung ating working range lang na linear, dun lang working yung ating Beer-Lambert's law. Kapag beyond this concentration, hindi na siya dependable. Okay? So it is part of the real deviation. Next is the chemical deviation. For the chemical deviation, it is due to the nature of the analyte and its interaction with other molecules. So ang ating assumption here is kapag nire-read natin yung ating samples sa UV-Vis, dapat walang chemical reaction na nangyayari during the reading. Okay? But possibly may interaction yun na hindi natin nalalaman. So that is part of the chemical deviation. Next naman is the instrumental limitations. It is the possible presence of stray lights and noise dun sa ating instrument. Okay? So again, isa-isahin natin sila. Yung sa real and chemical, ayan. So Beer's law is not applicable for analyte with high concentration as mentioned earlier. Next, under this condition, distribution effects and electrostatic interactions become significant. So ito yung nangyayari sa ating chemical deviations as well. Next, absorptivity now depends on the refractive index of the solution. Next is we have the instrumental limitations. The light that passes through the detector is actually polychromatic. So as you can recall, dun sa ating light source papunta sa monochromator, ang ating goal is yung ating polychromatic light ay once it passes through the monochromator ay lalabas siya as monochromatic light. Pero it's not always the case. Okay? So, yan ay part of the limitations ng mga instruments natin. Next is manner on how the reading is carried out. So yung ating cuvette, there are two sides. Meron yung opaque side at transparent side. So dapat yung light natin ay magpapass through sa transparent side only. Okay? Next is the presence of stray light. So yung light na galing sa environment na nagpumapasok dun sa ating system possibly can affect your readings. So yung stray light natin is the radiation from the instrument that is outside the wavelength chosen for the determination, often is the result of scattering and reflection of the surfaces of gratings, lenses or mirrors, filters, and windows. Okay? The next naman natin is how do we analyze using UV-Vis? So we have analysis of single component system and analysis via simultaneous of two component systems. So let's discuss the difference between the two. So sa single component, you can quantify the concentration of the solution by means of constructing a absorbance curve. So in here, the concentration of the analyte is determined by interpolation only. Okay? So it is mentioned here that we never use extrapolation. Next is for quantitative analysis, the absorbance of all the standards and samples should fall below 1. Okay? So yung mga absorbance na greater than 1, hindi na natin siya kino-consider. Alright? Then standards which have an absorbance greater than or equal to 1 are excluded from the calibration curve. Okay? So, dun sa ating understanding sa Beer-Lambert's law, di ba? Ang absorbance natin is directly correlated with the concentration. So, if you have an absorbance greater than 1, ibig sabihin, highly concentrated yung ating solution. So, if you have a absorbance greater than 1, what we can do is dilute that sample and read again sa ating UV-Vis spectrophotometer. Then after you have read, you have to take note of the dilution factor para ma-account natin yan when we quantify the concentration of our solution via interpolation. Okay? Next naman is for the simultaneous analysis. So ang assumption dito is the absorbance of the absorbing species is additive. Ibig sabihin, if you have sample A and sample B, tapos na-read natin siya ng magkasama, yung absorbance ni A and yung absorbance ni B ay additive. Total absorbance. Okay? Next naman is the analytes of interest does not react or interact with each other. Ibig sabihin, if we mix A and B, dapat wala tayong reaction. Sabihin, nagka-coexist lang sila sa ating solution, but there is no reaction between A and B. Hence, the absorbance of A and the absorbance of B can be determined simultaneously. Okay? So I will end the discussion now for UV spectrophotometer. For the next video, we'll have a sample problem and sample calculation. Okay? So thank you for listening.